Hello, in this video we will do 102 tutorial 7, and in this tutorial we have 3 different topics. The first one we'll talk about summation and product notation. Then we'll talk about variations of induction, not including strong induction. And finally we'll talk about strong induction. The reason I separated those two, well, strong induction is also a variation of induction, is because that I want to tell you the difference between normal induction and strong induction. Okay, so let's just start. We have summation and product. So let's introduce the notation. If we have am plus 1, am plus 2, all of those are real numbers, where your m and n are integers, and m is smaller than n, then this notation, the sigma notation, from I equals to m to n, and we add ai together, is am plus 1 plus all the way till am. The product notation is a pi notation, so it's the product of ai starting from I equals to m till n. So that's am times am plus, well, this is a typo, am plus 1, all the way till am. And here are the properties of the summation and product notation. The first one is that, wow, I noticed that I have a few typo. Here should be a c here. Okay, so sigma c ai equals to c sigma ai. That's the first one. The second one, we have sigma of ai plus bi equals to sigma of ai plus sigma of bi. So if you add them together first and then add everything and you separately add them, that's the same thing. Same for product, c of ai equals to c. This part is slightly different from adding them together, okay, because when you put c inside, you're multiplying c as well. So that's c to the power of m minus n plus 1 times pi of ai, and this is just really similar to this. Anyway, here is an example. So we want you to evaluate the value of the following expressions. The trick to do this is that you can compute the first few terms and see if there is anything you can cancel out. So you don't really compute this all the way till 99 manually. So when we know that we start from I equals to 10 all the way till 99. So when I equals to 10, you have 10 over 11 times when I equals to 11, you have 11 over 12. And when I equals to 12, you have 12 over 13. And all the way till when I equals to 98, 98 over 99 times 99 over 100. Okay, so if you write this out, you can notice that we can cancel those out. So eventually, so we don't have this anymore. Eventually, you'll get 10 over 100, which will give you 1 over 10. So that's the first one. The second one, again, let's just compute the first few terms and see if there is a pattern that we can do. So this will give us when k equals to 2, you have 1 over 3 minus 1 over 2, plus when k equals to 3, you have 1 over 4 minus 1 over 3, and so on, all the way till when k equals to, let's write the second last term, which is 1 over 19 minus 1 over 18 plus 1 over 20 minus 1 over 19. Okay, so if you notice this, you can cancel off some terms as well. So you have 1 over 3, you have minus 1 over 3, and you should have minus 1 over 4 somewhere in between. So that cancels out as well. And same here, this is gonna cancel out with a term in here. And 1 over 19 cancels out. So eventually this will give you negative 1 over 2 plus 1 over 20. Okay, and that's gonna give you minus 10 plus 1 over 20. So that's minus 10 over 20 plus 1 over 20. So that's 9 over 20. Wait, it's negative 9 over 20. Sorry. Yep, negative 9 over 20. Number 3, we have the sum of n times this whole thing. So let's calculate this first. So if you notice that m equals to 1 till 101, so you don't have any variable, which means every single term you have is 1. So that's the same as 1 plus 1 plus 1 plus 1, and you add it 100 times. Okay, so we can rewrite this whole thing to be 100. Alright, and now you can use the property over here. So we can use the first property, and we can take 100 out. So that's gonna give us 100 times sigma. Okay, so this will give us 100 times 1 plus 2 plus 3 all the way till 10. And we can use a formula that you learned from high school. So that's gonna be 100 times 1 plus 10 times 10 over 2. Yeah, so whatever you get, that's a big number. So that's 50 times 10 times 11. So hopefully I didn't make any calculation error. Yeah, looks good. Anyway, that's about product and summation. Let's move on to variations of induction. So again, let's recap the principle of mathematical induction. We talked about it already in last tutorial, so I'm not gonna spend any time on this principle anymore. So if you need a review, go back to the last tutorial. Now I want to talk about some variations of induction. So a few variations you'll see in 102. The first one is when base case is not when n equals to 1. So it might start from n equals to 2, n equals to 3, or whatever. Okay, so if you do start with n equals to 3 and you do induction, then whatever you proved, that's gonna be all natural numbers starting from n equals to 3. Alright, also we can have even number or odd number variation, which means they ask you to prove this is true for all even naturals, or this is true for all odd naturals. So those two are really common. Number 4 is a recursive sequence. Most likely you'll see recursive sequence in strong induction question, but sometimes recursive sequence is like a normal induction. Sometimes you don't need strong induction to do it. And I think there is one example in your textbook. So I'm not gonna do this, but because there is one example in your textbook, you can just have a look at this. I'm not gonna talk about separately because you will see recursive sequence again in strong induction. Okay, so let's have a look at the first example. They want you to prove that 2 to the n is greater than n squared for all n in natural number, where n is greater than or equal to 4. This means that 4 is gonna be your base case. So let's try this question. Let's proceed by induction on n. So first of all, I want to define what my P of n is. Actually, in this case, I'll write one proof that doesn't involve P of n, because you don't really have to. It's better that you do for your future courses, okay? For your Computer Science 236, I think that's the code. Anyway, base case is when n equals to 4. We have 2 to the 4 equals to 16. 4, wait, is this even true? For n greater than or equal to 4. I feel like I copied the wrong question, because 4 squared is 16 as well, so this is not even greater than. Okay, so I guess it's a typo. Here should be strictly greater than. So our base case starts at 5. When n equals to 5, 2 to the power of 5 is 32. Wait, is it? Now I'm confused. 32. N squared, 5 squared is 25. And we know that 32 is strictly greater than 25. So this base case holds. Inductive hypothesis. Suppose that 2 to the k is greater than k squared for some k in natural number where k is greater than 4. I think original question was greater than or equal to, but whatever, it's okay. Anyway, number 3, we can do your induction now. So induction step. I like to write down what I need to prove, so I'll write down we need to show 2 to the k plus 1 is greater than k plus 1 squared. Okay, so this is what we need to prove. So this is our end conclusion eventually. So let's start with the left hand side, 2 to the k plus 1. This equals to 2 times 2 to the k. The reason I write it like this is because in our inductive hypothesis you have 2 to the k. Okay, so we can use that. This is gonna be greater than 2 times k squared by IH. Okay, since we have 2 to the k here, it's multiplied by 2, so you can multiply by 2 on both sides. You'll get this by IH. Now, this can be written as k squared plus k squared. And I want to show this whole thing is greater than this. So let me make a side note. I want to show k squared plus k squared is greater than k squared plus 2k plus 1. So that means you need to show k squared is greater than 2k plus 1. Okay? So if we showed this, then we showed this. Then this whole thing is greater than this, which means this is greater than this. So this is what we need to show right now. So let me just do some rough work. This is the same as k squared minus 2k minus 1 is greater than 0. I can complete the square. K minus 1 squared. So that's plus 1 minus 2 is greater than 0. And we know that our k is greater than 4. Okay, so this k is greater than 4. So this is the same as k minus 1 squared is greater than 2. Hopefully I didn't make any computation error. Let me just check. Plus 1 minus 2 is minus 1. Yeah. Anyway, so since k is greater than 4, k minus 1 squared is going to be greater than, so 3 squared is 9, which is greater than 2. So this is true. So I'm just going to say this is strictly greater than k squared plus 2k plus 1, which equals to k plus 1 squared. And from here, by side proof. Actually, I'll just say by star and I'll write star at the bottom. So my star is just this in backwards. Okay, so I'm gonna start with since k is greater than 4, we know that k minus 1 squared is greater than 9, which is greater than 2. Okay, so that means that k squared minus 2k plus 1 is greater than 2. So k squared is greater than 1 minus 2k. Is it? 1 plus 2k, sorry. Yeah, you move this to the other side. K squared is greater than 1 plus 2k. So that shows that this step is true. Okay, so this is greater than this. So this whole thing is greater than that. That's my star. That's my set proof. So therefore, as required, therefore, by principle of mathematical induction, we know that 2 to the n is greater than n squared for all n in natural and n is greater than 4. That's the first example. Now let's look at the second example. We want you to prove that 3 to the n minus 1 is divisible by 8 for all even natural n. So again, proof. Let's proceed by induction on n. Okay, so let's talk about base case first. Since our n is a natural number, so natural means you start from 1, 2, 3, 4 and continue. And they said it's even natural number. So that means 1 is not our base case anymore, because 1 is not an even number. So our base case starts with 2. This case, I'm just gonna define my Pn so that my life is easier later. Let Pn by be 3m minus 1 is divisible by 8. Okay, where my n is natural n, is even natural, is even natural. Okay, so base case is when n equals to 1. So when n equals to 1, when n equals to 2, sorry, because it's even. When n equals to 2, 3 to the 2 is 9, minus 1 equals to 8, which is clearly divisible by 8. So base case holds. Now, inductive hypothesis. Inductive hypothesis. So I'm gonna suppose pk for some natural k. Okay, remember it's for some, not for all. And also, wait, I keep missing even here, okay, for some even natural k. So those are really important for some, and it's even, and it's natural, okay? Can't miss any of that. Induction step. We need to show that 3 to the k plus 2 minus 1 is divisible by 8. Why k plus 2? So we want to show p of k plus 2. Why k plus 2? Because we want to show for all even natural, and our k is a natural k, or is an even k, even natural k. If you use k plus 1, k is even, then k plus 1 is odd. Okay, that's why we need to add 2. So we want to show p of k plus 2. So 3 to the power of k plus 2 minus 1. So we want to show this is divisible by 8. Okay, I don't know if it's divisible by 8 yet, but I want to show it's divisible by 8. So this equals to 3 to the k times 3 to the 2 minus 1. Basically, I just wrote it, the exponent, and 3 squared is 9, so that's 9 times 3 to the k minus 1. We can write 9 as 8 plus 1. Times 3 to the k minus 1. Now you can distribute them. Okay, so that's gonna be 8 times 3 to the k plus 3 to the k minus 1. Why did I write 9 as 8 plus 1? Because I want to show it's divisible by 8. So if I write it in this case, I have 8 times 3 to the k. Anyway, this is gonna be, let me just add bracket here. Okay, now we know that this is definitely divisible by 8 because it's 8 times the integer. This is also divisible by 8 by our inductive hypothesis. So the sum of them must be divisible by 8 as well. So since 8 times 3 to the k is divisible by 8, and also 3k minus 1 is divisible by 8, by 8 by IH. Okay, we know this from your hypothesis. So the whole thing, 3 to the k plus 2 minus 1, which is the sum of them, must be divisible by 8 as well. Okay, so therefore, by PMI, P of n is true for all even natural n. That's the end of the proof. I left extra practice here. This question was my quiz question when I took MAT102, so try this. It's a good question. Anyway, strong induction. Now I want to talk about strong induction. Look at this principle, okay? You can see that the only difference between induction and strong induction is the hypothesis. This is a difference between inductive, is like the second condition. I mean hypothesis, I meant this part, okay? The normal induction says that for any k in natural number, pk implies pk plus 1. Strong induction, you make a stronger hypothesis. So you need a stronger hypothesis, which means that your hypothesis, instead of assume pk only, this time you're gonna assume that all of them are true. Still not for all k natural, but it's still for some k natural, but you assume everything before k and k itself are true. Okay, so that's the difference between induction and strong induction. And many of you will ask me, when do I use normal induction and when do I use strong induction? The key is that for any induction question, you can also prove it by strong induction, but not the other way around. A lot of time we use induction because it's simpler, but sometimes you need strong induction to prove a certain question. Okay, so when do we use strong induction? We use it when our induction step requires information about p of, let's say, p of 2 or p of k minus 1, p of k minus 2. Because normal induction only gives you information about p of k. If you need anything that's before this term, okay, so let's say p of k minus 1. The normal induction does not give you this information. You don't have that information, okay? So that is why sometimes you need strong induction. And here is an example. Actually, I want to do example 2 first because it's a recursive sequence. so that I can talk about recursive sequence, and we'll move back to example 1. So example 2. The sequence an is recursively defined by a1 equals to 0, a2 equals to 6, an plus 1 equals to negative 6 times an minus 1 plus 5 times an. Prove that by induction you have this. So I want to first talk about recursive sequence because it's useful if you're a CS student. This is a recursive sequence. Okay, so this definition, this an, how it defined, it's a recursive sequence. Why is that? Because your an plus 1 depend on the term before and the second term before. Okay, so an plus 1 depends on an and an minus 1. That's recursive sequence. In this case, you know that you need to draw induction. Okay, because what you need to prove, you'll see that you need to prove a k plus 1 equals to 2 times 3 to the k minus 3 times 2 to the k plus 1, sorry, k plus 1. Okay, you'll see that you need to prove this, but by definition of ak plus 1, you'll see that ak plus 1 equals to negative 6 times ak minus 1 plus 5 times ak. You'll see that when you use this definition, you actually need information of ak and ak minus 1. Normal induction only gives you what your ak is, but strong induction can give you what your ak minus 1 is as well. That's why you need strong induction. So let's try this question first. Proof. Let's proceed by strong induction. On n. Okay? So, base case. Base case, when n equals to 1, we have, so when n equals to 1, you need to check if this matches with your a1. So we have a1 equals to negative 6. Wait, what am I doing? You need to check this. So a1 equals to 2 times 3 to the 1 minus 3 times 2 to the 1. That's gonna be 6 minus 6, which is 0. Which equals to a1. That's given, so this is good. Now, some of you might ask, how do I know if I need 1 or 2 base case? Let's suppose we don't know. Let's say we don't know if we need 1 or 2 base case. Let's just do the next step. Inductive hypothesis. Actually, let's suppose we don't know we need to use strong induction, okay? Let's suppose we don't know. I'm just gonna write normal induction. Suppose, let's say ak equals to 2 times 3 to the k minus 3 times 2 to the k for some k in natural number. Suppose we don't know if it's strong induction or not. I'm just gonna write a normal induction. And I wanna show you when can you know you need a strong induction. So let's do inductive step. So inductive step, I want to show a of k plus 1 equals to 2 times 3k plus 1 minus 3 times 2 to the k plus 1. So this is what I want to show. Let's start from the left. So ak plus 1, by definition, it equals to this. Oh, by the way, k has to be greater than 1. But it's not important right now. Anyway, negative 6 times ak minus 1 plus 5ak by definition. Okay? Actually, let me erase this. I'll talk about that later. By definition, since we know this is how I defined. Now, the thing is, what do you do next? You want to replace your ak minus 1 and the ak here. Your inductive hypothesis tells you ak equals to this. Okay? So you can substitute this to here. But, what about this? What do you do with this? We don't know anything about this. Okay? You don't know anything about this. You don't know what's it equal to. So, eventually you cannot prove it. That's why you know that we need information about ak minus 1. How do we know that? If you make your inductive hypothesis a strong inductive hypothesis. Okay? So, you need information about that. So let's change our inductive hypothesis to a strong one. So suppose ak equals to that for actually I'm gonna write an instead. So let's mimic what's written in your textbook. Suppose an equals to 2 times 3 to the n minus 3 times 2 to the n for n equals to 2, 3, wait, hold on. For n equals to 1, 2, 3 till k. For some k that's in natural number and k is greater than 1. Let me check if that's how your textbook write it, because that's not how I usually write it, but I want you to follow the textbook. Yeah, assume the theorem is true for that. Yeah, that's how your textbook write it. Okay, anyway, so in this case that we can know what our ak minus 1 is now, because you can use your inductive hypothesis, put k minus 1 here. So okay, so in this case you know ak and you know ak minus 1, so that's gonna give you negative 6 times ak minus 1, which is 2 times 3 to the k minus 1 plus 5, oh, that's not complete yet, minus 3 times 2 to the k minus 1 plus 5 times 2 to the 3 to the k minus 3 times 2 to the k. So this is by IH. This will give us negative 6 times 2 times 3 to the k minus 1 plus 6 times 3 times 2 to the k minus 1 plus 5 times 2 times 3 to the k minus 5 times 3 times 2 to the k. Basically, I just open the bracket, but I want to collect the like terms, so I want to collect this. Oh my god. I want to collect this, and then this and this. Note that they're not the same yet, but I want to connect them. So negative 6 can be written as negative 2 times 3. So negative 2 times 2 times 3 times 3 to the k minus 1. And you can combine those two together. That's going to give you 3 to the k. Okay, plus 6 can be written as 2 times 3. So 3 times 3 times 2 times 2 to the k minus 1. Again, you can combine those two together. That's going to give you 2 to the k. Plus 5 times 2 times 3 to the k. Minus 5 times 3 times 2 to the k. Now you can collect them. So, this and this, they are in the same group. Okay, and this, let's use another color. And this, they are together. Okay, so you can add them together. Let me use orange. So negative 4 plus 10 is 6. 3 to the k. Minus or plus. That's 9 minus 15, so minus 6 times 2 to the k. We are not done yet. We want this, remember? So we want 3 to the k plus 1 and 2 to the k plus 1. That's going to give you, again, 6 can be written as 2 times 3. So 2 times 3 times 3 to the k. Minus 3 times 2 times 2 to the k. Those two and those two can be combined together. So eventually you get 2 times 3 to the k plus 1 minus 3 times 2 to the k plus 1. Okay, so that's exactly what you need. Now let's go back. At the very beginning, I said, let's suppose we don't know how many base case we need. Now let's go back and check if we need more base case, okay? Since we added, we changed our inductive hypothesis to a strong one. We changed this. So let's look at the inductive hypothesis and see if anything makes sense. Now, notice that for inductive hypothesis, our k is greater than 1. Which means that our k cannot be 1. Okay? It doesn't work when k equals to 1. That means, recall our principle. We need to have p of 1 implies p of 2 implies p of 3 and so on. Okay? It doesn't work when k equals to 1. So we don't know p of 1. At least for inductive hypothesis, you can have p of 1 implies p of 2. Since you don't have p of 1 implies p of 2, we don't have this process. So we checked p of 1, this is true, but we don't know if p of 1 implies p of 2. Okay, because k is greater than 1, it cannot be 1. We checked in base case that this is true, but we don't know if this whole thing is true. Okay, we cannot know. That's why you need to check p of 2 as well. So in this case, you would check p of 1 and p of 2. And then p of 2, we know this implies p of 3. P of 3 implies p of 4, and so on. That's why everything would be true. But you cannot show that P of 1 implies P of 2 because our K here is greater than 1. So that's why we need to check P of 2 as well. So let's check P of 2. When n equals to 2, A2 equals to 2 times 3 to the 2 minus 3 times 2 to the 2, which is 3 times 9 is 18, minus 3 times 4 is 12, which equals to 6. And that equals to the A2 that's given, so that's true. Okay, so now you see that I explained why we need two base cases. Okay, because we cannot have, for our inductive hypothesis here, you cannot show that P1 implies P2. So we need to check both P1 and P2 and use P2 implies P3 and so on. So that's why we need two base cases. Why do we need strong induction? Because here, okay, you need information of both AK and AK minus 1. Normal induction only gives you information about AK. You need strong induction to give me information about AK minus 1. So that's why we need strong induction. Let me just conclude. So therefore, by principle of strong mathematical induction, Pn is true for all n in natural number. Alright, now we can go back to example 1. This example is slightly more complicated than the other one, although this one doesn't have a recursive sequence. But okay, again, suppose that we don't know if it's induction or strong induction. Okay, so I'm just gonna write normal induction and say if we can use normal induction to prove it. Let's proceed. By induction on n. Okay, I always write this sentence because sometimes you have more than one variable, and sometimes you might be confused which one do we do induction on. For example, in this case, you have x, you have n. Which one do you do it on? Okay, well, you know that we're gonna do it on n because you need to show this is true for all n in natural numbers. We do it on n because x is not changing. X is a real number. Anyway, base case. Again, I'm doing it as I don't know if it's induction or strong induction. But I'll show you why we need strong induction in this case. So base case, we have n equals to 1. We have x to the 2 plus 1 over x2. This is an integer. This is given, so this is true. Inductive hypothesis. Suppose x to the 2k plus 1 over x to the 2k is an integer for some k in natural number. Okay, so that's my inductive hypothesis. In the induction step, I need to show x to the 2k plus 1 plus 1 over x to the 2k plus 1 is also an integer. That's what we need to show. Alright, but now, where do I even start? I don't know anything. I don't even know where to start, okay? But one thing one thing I do know is that if we add two integers together, we get another integer. And if we multiply two integers together, we get another integer. If we subtract two integers, we get an integer. So I want to start from there. So I'm gonna start from here. I'm gonna use my base case. Actually, I want to do some rough work because I want to show you my rough work and how I got everything. Okay, let me do rough work. So I want to show this is an integer, and again I want to write it as two integers adding together or multiply together or subtract each other. So x to the 2k plus 2 plus 1 over x 2k plus 2. This is gonna be slightly harder to everyone, I guess. 2k plus 2. So I wanna use x to the 2k plus 2. I wanna add a number and then subtract a number, okay? Plus x to the, we know 2k. We know 2k, we know information about this, we know information about this. If you multiply them together, that's gonna give you 2k plus 2. Actually, let me multiply them together and see what we get. X to the 2k plus x to the 2k, x2 plus 1 over x. That's gonna be x to the 2k plus 2 plus x to the 2k times 1 over x, so x to the 2k minus 2 plus x of 2 minus 2k plus x of minus 2k minus 2, so minus 2k plus 2. Okay, so here we have 2k plus 2, which we have already, 2k minus 2. So let's add 2k minus 2 plus x of 2k plus 2 plus we have x of 2k minus 2, so we have this. This is this. Okay, so x of negative 2k plus 2. And here we have more things. So we have this, which is here. We have this, which is here. We need 2 minus 2k. So let me add x of 2 minus 2k and plus x of 2 minus 2k. Okay, so I got all of those by multiplying them together. So that's gonna be x of 2k plus 2 plus x of 2k minus 2 plus x of 2 minus 2k plus x of negative of 2k plus 2. So I know those four terms will give me the product of those two numbers. So we have this, 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 and this. This, and 2k plus 2, 2k minus 2, minus 2k plus 2, and 2 minus 2k. Okay, here. Okay, those four terms will give us a product of those two terms, and we know this is integer. Okay, because this is integer and this is integer. So we have two terms left. And let's see if we can write it as something else. 2 minus 2k is negative 2k minus 2. Wait, did I? Oh, here is minus. What am I doing? Because we plus 2k minus 2. Well, we plus and minus. Oh my god, I made so many typos. Here is minus. Sorry guys. Minus. And plus minus. Here's minus as well. So, like this. Anyway, so I made the product of those two, gave those two for terms. I know that I have this term already. I have this term already. I don't need those two terms, so add them and minus them. So that's 0. Okay, add them, minus them. And I group them together. That's gonna give me the product of those two. So let's see if this can give me anything. This will give me, again, this orange part will give me x of 2k plus 1 over x of 2k times x of 2 plus 1 over x2 minus this. If you notice that x to the 2k minus 2 is x to the 2k minus 1. Okay, and this will give you x to the negative 2k minus 1. So that's the same as x to the 2k minus 1 plus 1 over x of 2k minus 1. So those are the same thing. And if you notice that, okay, if we know this, let me change a color. If we know the green part, I use green for formal proof. Let me use another color. If we know the which color? The brown part. If we know the brown part is an integer, then the original is an integer. Because this is integer minus another integer will give you integer. So we need to show this is an integer. How do we know that? Well, if your hypothesis is a strong hypothesis, then you know information of pk minus 1. Well, p of k minus 1 will give you x to the 2k minus 1 plus 1 over x to the 2k minus 1. That means to show this is an integer, we need strong hypothesis. So let's change the hypothesis to a strong hypothesis. For, let me use n here. For n equals to 1 to 2k, for some k in natural number, okay? Here your k don't have any restriction, so for some k in natural number. Now we know that this is also integer, so let's write our formal proof. X to the 2k plus 1 over x to the 2k times x to the 2 plus 1 over x to the 2 minus x to the 2k minus 1 plus 1 over x to the 2k minus 1 equals to x to the 2k plus 2 plus x to the 2k minus 2 plus x to the 2 minus 2k plus x to the minus 2k plus 2 minus x to the 2k minus 2 plus x to the negative 2k minus 2. And then this is the same as x to the 2k plus 2 plus x to the 2k minus 2 minus x to the 2k minus 2 plus x to the negative 2k plus 2 plus x to the 2 minus 2k minus x to the 2 minus 2k. Okay, so those cancels out. You get back to whatever we need to prove. Wait, I just realized something. This could be our formal proof already. Sorry guys. Let me just delete this. This could be our formal proof already. Okay, here. We can write this as this. X to the 2k plus 1. Okay, so we need to show this is an integer. We can write it as integer minus an integer. So that's gonna give us integer already. So since x to the 2k plus 1 over x to the 2k, x squared plus 1 over x squared, x to the 2k minus 1 plus 1 over x of 2k minus 1 are all integer. Okay, by base case and IH. Okay, therefore this whole thing should be integer as well. And that is saying that this is an integer as well. Me move it to the top a bit. Okay, since this is integer by PMI, by principle of strong mathematical induction, x to the 2n plus 2 plus 1 over x to the 2n, not 2n plus 2. The original one is 2n. 2n is an integer for all n in natural number. Okay, it took us a while. Some of you might ask me, do we need 2 base cases? Well, you don't. Why? As I mentioned before, I explained why we need 2 base cases here. Because here you cannot get P1 implies P2. But in this case, okay, your K here can be any of the natural number because you don't have any restriction. Okay, you don't have any restriction in the original question. That means you can have P of 1 implies P of 2. So you don't need to check if your P of 2 is correct. So in this case, it's a strong induction question, but you only need 1 base case. Anyway, that's the end of the tutorial. I am sorry that I had to send my cat to the vet. It's unpredicted. Anyway, I will see some of you tonight at 8 p.m. for office hour. Again, sorry for this. I will try to make sure this doesn't happen again. Okay? Bye for now.